Alrighty, I think people are still trickling in, but we'll go ahead and get started. So thanks for coming, everyone. This is the quarterly meeting of the Microplastics Subcommittee. It's part of the California Water Quality Monitoring Council. I'm here with my co-chairs, Dr. Monica Arienzo and Shelly Moore. So just a little bit of background. I know not everyone here has been to previous meetings, so bring everybody up to speed. This subcommittee is largely formed around efforts that are ongoing in California, but applies elsewhere. We have two legislative mandates that are relevant to the work that we're doing and really driving a lot of the research. One is Senate Bill 1263, which requires the Ocean Protection Council and the State Water Board to assess risks of microplastics in the marine environment, among other things. And we adopted a statewide microplastic strategy earlier this year that is laying the foundation and the plans for the research that we need to get done. We also have Senate Bill 1422. This requires the State Water Board to address microplastics in drinking water. In 2020, we adopted the definition of microplastics. And then just yesterday, we adopted a policy handbook that sets forth the plans for monitoring in tap water and source water over the next 4 or so years. And I'll give you all an update about how that went and what the details are later in the agenda. And like I said, this subcommittee it's loosely formed around these or it's driven by these mandates, but it's also a global community and it's open to everyone. Right now, we have 3 co-chairs, myself, Monica Arienzo, and then Shelly. And really, this is just a community that shares information and pushes the research forward and coordinates with management. So some of the platforms that we're using right now to share information include a shared library on Zotero. We have code repositories that are shareable on GitHub. We also have a Google Drive that contains all of the slides and content from previous meetings. Anybody can go in and add content as well. It's just this bit.ly link right here. So I can drop that into the chat. You can easily access it. Related to this effort, but not directly managed by the subcommittee, is the Plastiverse. This is a relatively new project that I started with Dr. Wen Cowger, Leah Thornton-Hampton, and a few others. And really, the goal of this website is pretty similar to the subcommittee. It's an open access platform that is trying to remove barriers on plastic research to everyone. And this is just a little preview of sort of what the website contains. It's right now it has a filterable toolkit. So you can look for, say, you're trying to look for a sampling device. Today we're going to be talking about this portable catamaran drone. You can easily find that on the Plastiverse. So check it out. If you have something, if you're working on a project or you know of something that needs to be on the website, there's a way on there to send us that information and we'll get it on the website. This subcommittee is pretty balanced in terms of representation. We want to maintain that balance and include folks not only from the industry side, but also academia, NGOs, government. And so you can see here, it's a pretty good makeup. We had 173 attendees at one of the previous meetings. And the work that we're doing, like I said, it's largely driven by management, but we have a lot of different priorities with this group. It's fairly broad. The 3 highest priorities based on a recent poll were focused on sampling collection, analytical methods, and then communication strategies. So those are the 3 efforts that we are currently focusing on for our subgroups. And so that brings me to the agenda for today. We've got a lot of great speakers today talking about different sampling techniques, everything from tap water to some pretty innovative ways to collect microplastics out in the open ocean. And so with that, I'm going to hand it over to our first speaker, Lindsay Darjany at the Moore Institute for Plastic Pollution Research. And I believe Lindsay's a co-host. If not,
yeah, thank you. Give me 1 second. Okay. Okay, can everyone hear me? Okay.
Sounds great.
Great. So, hi, so my name's Lindsay. I'm a research scientist with the Moore Institute for Plastic Pollution Research, and we are a fairly new nonprofit dedicated to studying microplastics in all environments, but mostly these aquatic environments. And so today I'm going to talk to you about one of the devices we've been working on, which is called the Tap Trap. And this is a simple sampling device for studying microplastics, collecting them, trapping them, not just in tap water, but any other type of water system or inline system that someone might be interested in. So I wanted to just take a step back and, oh golly, there we go. Sorry, my PowerPoint, there we go. And look at sort of plastics in drinking water in general. And so although we know that, the microplastics in drinking water is not the largest source of ingestion, it's really important because we know that microplastics are entering our watersheds, they're contaminating our waterways and eventually ending up in the water systems that provide our drinking water. And we know that the US has the largest tap water contamination rate, but more data is really needed to understand the extent of microplastic pollution in these different pathways in our drinking water. And so I'm excited for this group because California is really the leader in this field. But with these type of studies, we know that there's lots of complex issues. And so we're focused on the collection part of those complex issues, but we know that, these methods are nuanced, they're time consuming, they can be expensive. And that's really where we're focused, is creating this sort of multi-tiered approach to answering the questions that come with the challenges of collection. So how do we sample and collect enough drinking water to accurately determine microplastic contents? We're looking at combining visual microscopy with FTIR to identify plastic particles. And then we're looking at how do we analyze, gather, and then share that data to really put together a great snapshot of what are in our water systems at different points and in different pathways. And so what we're focused on right now is this collection part of it. And so in order to sample for microplastics, you need a lot of water. Let's just say you need 100 liters per sample. Ideally, you'd want to limit the number of different bottles because prepping, filling, and shipping lots of different vesicles would introduce plastic pollution. And ideally, you don't want to sample in plastic, you need glass or something else. And so, if you think about that, 100 liters is 4 6-gallon glass carboys, which would be really expensive to ship, it'd be really heavy. And so what we've come up with is this collection device that we're calling the Tap Trap to sample microplastics found in drinking water, but again, on any other inline system. It's very versatile in how you can adapt it to maybe look for microplastics in whatever you're interested in. So traditionally, samples are collected on some type of filter, which oftentimes has a plastic content itself. It has the potential to introduce contamination. So what we've devised in our lab is this sampling device that actually connects to any inline system or tap water system. It collects fibers on a stainless steel mesh. You can then cap it and send it back for transport. It's equipped with a flow meter to measure the volume of water passing through the inner filtering unit. And ideally, our focus is to make this something that's easy to use, that's not that expensive, and in our field has the potential to be reused over and over again. And so what this inner filter looks like, it's this device devised to capture particles and fibers about 20 microns or greater. So this is like regular aerator on a sink. That usually has a pore size of just a couple millimeters. And so below that, you would attach this tap trap. And so the aerator is sort of like acts as a pre-filter. Then you have our filter that sits inside this component. And so this is a stainless steel mesh filter that captures fibers and particles that can then be capped and then sent back to us to get analyzed. We've been experimenting with different types of mesh sizes and different weave types. And so in these pictures, it's a little hard to see, but you have a plain basket weave and a Dutch weave. And even though both of those mesh screens are designated as a 20 micron pore size, what we have found in the lab is that the parallel screen orientation of the Dutch weave actually traps and keeps particles and fibers at the surface. And so then we can actually take those filters straight to the microscope and then straight to the FTIR for testing. We've been testing this in our lab. We have a lab in Long Beach. It's small but mighty. We're equipped with an FTIR and a compound fluorescent microscope. We have pretty much full capability in there. And what we've accomplished is 75% and greater recovery rate using spike samples with known quantities of these little small blue spheres and also surrogate fibers. So after we've received that device back, we can actually take that filter and put it straight under our compound fluorescent microscope. And what we've done is we've actually optimized our microscope to automate photo documentation of the particles on the filter in just a few minutes. So it takes just a few minutes to actually get a really high quality image of the entire filter. This will allow us to have an initial record of particle morphologies, color. It will allow us to quickly quantify everything before further processing. So oftentimes in the transition between collection, microscopy, and then putting those samples on the FTIR, you're either picking them out or transferring them somehow. But this method will allow us to first just get a really quick snapshot of what's there. And depending on what type of information someone might want, this might potentially be enough. Okay, we could also use different polarization techniques or Nile red to determine the type of plastic. This would provide quick information depending on what's needed. We go to the next slide. So the main thing that we have in our lab is our FTIR. And so we will be using Fourier transform infrared spectroscopy to analyze the samples directly on the filter. And so we can quickly create a map of particles on the filter along with their spectral analyses. We can use those to identify the or quantify the material. And this is really the most reliable and cost-effective analytical tool for identifying plastic polymers or, assessing the quality of plastic materials. And so in the end, we could provide a rough report of quantity, type of plastic, and then a map of those plastic particles that you could pair with your photo documentation. This will also be relevant if you have, a really mixed sample where you're going to need to identify multiple different types of unknown polymer types, or if there's lots of different morphologies. And so we're really focused on the sort of the end of the line, what's coming out of tap water. This could be used to look for microplastic contamination in any inline system. And a lot of research laboratories have water systems that they might use for different experiments or filtered water for their lab. And so we hope that this little tool could be used for potentially different environmental laboratories. It could be used for nonprofits in science and education. Maybe they're interested in looking and some type of water system they are using. We've also had some interest from local colleges to use it for student projects. And so that image is actually one of our students from Pasadena City College that will come and use our laboratory for their student projects. So in the end, we hope that this data, sort of all the data that we would get from the use of the TAP trap would be added into the microplastics data portal. So together, this would give us sort of a holistic look at where that water, maybe what type of microplastics get added in the process, what comes out of the tap, what's maybe in a water system. But ideally, it could be integrated into that to inform decisions in the long run. So if you have any interest in this, or know of any other groups that might be interested in getting one of these devices, we're currently in the process of making a lot of them to share, because we're interested in that data. We want to know, what gets introduced in between the source and the output of water. And that's kind of where our interest lies. So yeah, feel free to contact me, Lindsay, at More Plastic Research, and I can tell you more about it. Or if you're interested in seeing how it works, yeah, just send me an email. All right, that's all I have.
Thanks, Lindsay.
Yeah.
And if anyone wants to ask questions, we can hold a couple minutes for that.
I think there was one. Oh, nope, you're good.
So people should be able to unmute themselves, raise their hands. You can also just use the chat if you like. Feel free to ask Lindsay questions.
I have a question.
Yeah, hi.
Thank you so much for your presentation. I'm curious about the sample size that you were able to process with this small filter. Can you speak to that?
Well, right now we're just running like in tap water samples. So we've been running about 20 to 50 liters of water, but depending on the content, I think it could process quite a bit more.
Yeah, do you find that there's a buildup of
not much in our system, but potentially in other systems there could be, and that might be that might be the case in which you might need like a pre-filter, which honestly, like I see in the future the potential to like layer these filters to almost get like a size fractionation within the device. Like that would be very easy to fractionate those layers so that you could get like a 70 micron, 20 micron, and even we've experimented, I forgot to mention it, with using a 5 micron mesh filter that would get those lower size classes.
Thank you.
Yeah, someone just asked about that. Yeah, we have been experimenting with the 5 micron.
Eric, you have, okay.
Hi. Sorry. Hi.
Hi, Lindsay. Question, have you thought, first thing is, are you creating a visual database of these samples?
We will be. We haven't had any yet, but yeah, that would be a great addition, even to get sort of a map of what different outputs look like in different areas. That would be really interesting. But no, we don't have any real use of this yet out in the community.
I would be interested. One is using the application of this with artificial intelligence, using if you had a large database of using known versus unknown samples to be able to actually classify anything that runs through it once you have a substantial database created.
Yeah, I think that would be really, really interesting, because yeah, it could be pretty easy to do something like that where you're determining like a cellulose particle from a plastic.
Well, yeah, and if you did a deep learning model, you'd not only be able to identify it, you'd actually be able to quantify its space in the in that domain.
That would be great. I don't know how to do that, but I'd love to chat with you if that's something you have expertise in. That would be really, really cool.
Yeah, I'd be interested.
Okay, great.
Our machine learning spectroscopy wizard, Wynn Cowger, is not here with us today, but it sounds like he'd want to connect with you on that, Eric.
Great. Robin.
Yeah, I have a few questions or comments about the sampling device. So it looks like it's on a threaded hose bib, but most of our sampling taps are not threaded for RT-PCR. And I also wondered how much pressure is required to get through the filter sieves, because if we don't have enough wellhead pressure, we're going to have to add a booster pump. And so I was just curious about those two items.
Yeah, we haven't done much adapting yet, but I would imagine that you could easily adapt that with like another like hose barb to some type of tubing that might fit a different application. And I'm not sure about the pressure question. We've been doing pretty mild experiments with our lab tap, but yeah, that would be something to definitely test in the future.
So let's just take one more quick question. Rick's got his hands up.
Yes, hi, Lindsay. So the meshes themselves, I assume they're reusable, or are they disposable? If they're reusable, what is the procedure for washing it to be able to reuse it? That was really my primary question. And then once you send it to the lab, and then you send back the mesh, and then who is the provider? Are there more than one provider? Is there a lot of availability of these meshes for a lot of sampling?
Yeah, that's a great question. So we're, sorry, your first question about being reusable, they're really inexpensive to make. We could essentially use like a die cutout to stamp out. At this point, we're using like a 25 millimeter width of a circle, but I don't know at this point if it would. I mean, yeah, we would. My hope is that we would reuse them, but they are stainless steel, so we could potentially just recycle them. They're very inexpensive per filter to make. And to what was your second question?
Oh, just the in this day and age, availability of supply. So where are you buying these from? Are you making them yourself? That was that second question.
Yeah, so we're actually making these in-house, and we have a few different vendors that are supplying the parts. They're assembled and checked in the lab, and we're hoping to send out, like, usually people would want like replicate devices. So we would send them the flow meter with the hose and all the tri-clamp parts, but then send them multiple collection devices that they can take replicate samples, or maybe they have, different variations. But as of now, we're purchasing the parts from a few different places and then making them in-house.
All right, thank you.
Yeah.
All right. Looks like you have a lot of questions to answer in the chat. So I appreciate if you could do that. And then we'll
Totally.
get to our speakers. So Andrea Faltynkova and Artur Zolich, correct me if I mispronounce your names, but our next speakers, and they're from the Norwegian University of Science and Technology. I actually met Andrea in Athens earlier this year and learned about some really cool work that they're doing. So I'll just hand it over. Make sure we can present.
Can you hear me well?
Yeah, sounds great.
Okay, great. Get the screen share organized here. Okay, does that look all right?
Yeah, it looks great.
Okay, perfect. Yes, thank you so much for inviting us here. Really great to be able to join you. My name is Andrea, as Scott mentioned, and my colleague who's also with us here is Artur. And we're gonna share some information about our little friend here, who we call Pamela affectionately, of Baywatch fame. And so you might be able to guess why very shortly. But I'll just introduce myself and Artur a little bit more I personally have a chemistry background, and I work in using hyperspectral imaging to analyze microplastics as a part of my PhD at the Norwegian University of Science and Technology, also known as NTNU. And throughout the course of my PhD, I've met Artur, who is actually a cybernetics postdoc. And we started collaborating on this project to try and create a more effective system for sampling microplastics in open water. So his specialty is really creating robotic solutions for applications specifically within the natural sciences, geared towards marine science. So I'm sure folks are familiar with kind of these horizontal trawling methods, either using mantas or horizontal plankton nets to collect microplastics. But for this, you obviously need a boat and a lot of logistics to kind of set you up. So we wanted to kind of do away with the need for that. And Artur came up with this solution, which is essentially an autonomous manta net that can be driven remotely. It's an uncrewed vehicle that works just like a drone. So you can drive around on the sea surface, and it became the portable catamaran drone, or PAMELA, as we now call her. So just a basic introduction to kind of the operating parts and how it works. We have these lovely Baywatch pontoons, which are right now off-the-shelf buoy components, actually for life-saving. So those have been converted into this catamaran structure, which then holds the electronics. So here we have a board that controls all of the autopilot and the propellers and all that stuff. And then on the opposite side, we have the housing for the battery. Then we have the net opening. So this kind of metal rectangle is where the manta net would be fastened, and then it would kind of drag behind. And you see that the opening is set forward. So it's kind of the first thing that's hitting the water. And the opening can also be changed for different applications. So we have this kind of typical horizontal cross section where you get the surface layer, but you can also change the orientation to get a deeper profile of the water. And of course, the size is quite flexible. These are all pretty simple parts to make, so that could be customized as well. There's the propeller on the side. So these are two propellers, one on each side of the buoys that power the vehicle from the battery on top. And there are two kind of primary modes of operation. So the first one is kind of what I call the remote control car mode. That's you just, controlling the vehicle manually from an interface either on a tablet or a smartphone or a radio controller. But the thing that's really interesting is that you can also put it on autopilot mode. So you can go into an open source application and create a path on a map in a very kind of quick and easy way to use. And then the vehicle will autonomously carry out that path once you set it on its way. So you just throw it in the water, push start, and then it follows the pre-programmed path. And the great thing about this is that multiple units can follow that same path. So here we're increasing the replicatability of the samples, and we're also minimizing the time used for the samples because you can have multiple units operating simultaneously. So here on the right-hand side, you can see the little yellow icons, which are the boats or the PCDs, the portable catamaran drones, which are following one another in this nice little circle that we sent them on. So here's just a quick demonstration of how it operates. This is me picking it up and throwing it off the shore. And then once you start it on its automated path, it goes completely on its own. So you have very limited support in this situation. This is operating from shore. And then the alternative would be to operate from either a small vessel or a large vessel. So you can imagine perhaps you're going out to do some sample retrieval. Maybe you have some passive samplers in place, or there's some other things that need to be maintained. You could throw this off the side, let it do its path, and then go and do your other work while it's collecting a sample. And when it's finished, you just go pick it up and collect your sample. So this is kind of enabling a little bit of multitasking here. There's also an actuated opening. So this allows for selective sampling. And this is especially relevant if you're close to a boat or the shore and you don't necessarily want to catch any contamination from either the vessel or the shoreline. And if you're more interested in an area that's a little further away. So you can raise the opening, send the catamaran drone out to the area you'd like to sample, lower it, collect the sample, and then raise it again on the way back. And there's another huge bonus with this, and that is that when you're on field work, sometimes it can be a little rainy and a little tough. And lucky for us, we have Artur, who is actually connected via LTE. So while we were sitting in the rain in Norway, he was sitting in his office in Poland, and he could actually control the drone from Poland because he's operating through this LTE network. So if we ever had a problem or something went wrong, he would just log on, check out the logs, check out what was happening, and then he could even steer it back to land for us if we were unable to do so. And then the one question that I always get that I want to nip right in the bud, people always ask, how does it do in the wind and the waves? And the answer is pretty good and also better than us. Things got pretty wavy on the shore here. We were launching and collecting PAMELA from a rocky shoreline, and it got a little bit too slippery and too dangerous for us to safely do that. But PAMELA, she kept driving, had no problem. So it turns out she can take quite a bit. But also the relevance of sampling in this kind of sea state is maybe a little bit questionable. But at least we know that she can handle a little bit of waves. We also developed a little bit of a different cod end system. So here we have a kind of like metal filter that has been custom made so that we have multiple filters, and this precludes the need to do any sample treatment on site or in the field. So we essentially would just switch out these metal cod ends, of which we had many, and then we would throw a little lid on them and take them back with us to the lab so that any sample handling was happening in a much more controlled environment. So the current applications of this drone right now, it has been used for microplastic. It could obviously be used for phytoplankton and zooplankton because it is essentially just a horizontal net, and the mesh size of the net can of course be changed very easily. And there's another PhD at NTNU who is working on salmon lice, and he's used the PCD to collect samples of salmon lice larvae that he's going to analyze for DNA for the presence or absence of larvae. Some kind of future directions we'd like to go. Right now we're looking at the integration of environmental sensors, so getting CTD data on it as well. And then looking at the ability or the potential to have some sort of vertical casts, either for CTD data or for a vertical phytoplankton cast as well. So just to quickly kind of summarize the benefits, we kind of feel that you could operate 3 vehicles comfortably with very limited support, and then you could get essentially 3 samples for the price of 1 in terms of your time and your effort. You do not need to be trained very extensively to pilot this vehicle. It's very easy to use, and it's built with the user experience in mind, so to speak. So having that remote expert user support allows you to be in the field very independently. There's no boat required, and you might reduce also the boat time required if you can send this out from a small vessel. And so that is going to save you obviously logistics and money on someone driving the boat and the fuel on the boat, which then of course brings us to the fact that this is a much lower emissions way to sample. So instead of using a 30 or 150 horsepower engine, we're doing it with 2 horsepower and an electric motor. And this will save you tens of liters of fuel. And I think Artur made a great little calculation here. I think we use the equivalent of 77 milliliters of fuel to do 7 hours of work. So a bit of a difference there. So the something I'd like to just kind of touch on here in terms of the opportunities that we are kind of like looking towards, we would love to get on doing some different sampling campaigns. Also would love to demonstrate the use of this in different applications. We're looking definitely at future projects and applying for different, right now, Norwegian projects. And we want to kind of push really the hardware and the software customizations. Right now we're using a lot of off-the-shelf parts, and we'd really like to make those pieces a little bit more fit for purpose. And then lastly, we are definitely looking at services. So kind of being able to facilitate the use of this unit. I think there was a slide that was missing some information, but I'll just fill you in that right now we don't necessarily have like a model for operation. And that's something that we're kind of developing in the moment. We are currently still a part of the university, so there's no company based on this or anything like that. But we are looking at the potential to do a not-for-profit organization, and then it would be much more of a anything as a service kind of style. That's what we're leaning towards. So we really like the idea of going more of a social enterprise direction with this project. And yeah, essentially our target price to keep the units relatively affordable would be under $5,000 US. Sorry about that missing information. And yeah, this is just kind of a highlight of how easy it is to operate. We had some of my colleagues' children joining us on fieldwork, and these kids have grown up with gaming and the internet, and they are very well versed in how to use a joystick, and they had no problem operating the catamaran drone. So this is Liv, my colleague's daughter, who is 8 years old, operating the PCD. So you can bring your kids. So with that, I'll just say thanks, and yeah, we can have some questions if there's time.
Absolutely fascinating. Thanks so much for sharing, Andrea. So if anyone has any questions, feel free to raise your hand. If not, we do already have a couple in the chat. I guess I'll start with one of them from the chat. Ezra Miller asks, how long does the battery last and how much sampling can you do before having to replace or recharge it?
Yeah, great question. So right now the battery that's in there lasts 1 hour. And if you're trawling for, let's say, 20 minutes or so, then you could definitely do 2 runs on 1 battery. We've been changing the battery every time just because we haven't really tested the absolute limit, and we definitely don't want to lose the vehicle. But yeah, so if you have multiple batteries with you, the great thing about this is that you can interchange them and send them out, send the device out again. So it runs on a Makita battery, which is one of Artur's, I think, stroke of genius. The Makita battery is really powerful, and it can be transported on a regular airline as carry-on. So there are no restrictions in terms of sending it, which is great. And then it allows you to have kind of an arsenal of charged batteries. So if you send it out for multiple runs, you're just swapping out the batteries, and you can easily operate for up to 8 hours. So we were doing some field sampling, and we were operating for 8 hours, and we had 8 batteries with us, and definitely never depleted any of the batteries.
Very cool. Again, people can just like raise their hands or just unmute. I'm going to read from the chat. So we've got another question. What is the smallest mesh size that you've used so far?
Yeah, so we used 120 microns, I believe, Artur, correct me if I'm wrong, for the salmon lice larvae sampling. And of course, the kind of speed and the mesh size of the net have to be a little bit paired in order to not get too much backflow. But the speed can also be changed. So we have it right now operating anywhere between 0.5 meter per second to 1 meter per second, but this is also something that can be changed quite easily.
And then have you noticed any turbulent interference between the pontoons and the net opening? This person's wondering how the collection rate compares to a typical manta net.
Yeah, so this is something we haven't had the opportunity to do, is to kind of directly compare the methods, and definitely something I'd be really interested in. The net is really the first thing hitting the water because it's set in front of the pontoons. So in this sense, we expect that the samples collected are going to be less affected by contamination because, you know, there's not really anything around to contaminate, like a boat or all that kind of stuff. But also you'll have less disturbance of the surface water layer because of the fact that there is no wake in front of the device. It's really hitting the surface water first with the opening of the net. And that is kind of the intention. For sampling salmon lice, we had to kind of change the net orientation, and then some things changed with the balance. So we had to kind of improvise a solution. And that was that one photo that you might have seen where the net was set behind the pontoons. But for microplastic sampling, it is the first thing that's hitting the water.
Wow, so many things to consider.
Yeah.
I think we're in the sake of time, we're going to go on to our next speaker. Andrew, if you want to just reply to people's answers in the chat, that'd be great.
Yeah, absolutely, will do. Thank you so much.
Yeah, thank you so much. I really appreciate you sharing with us, and I know it's a little bit late in Norway, so thanks for staying up. So our next speaker is Jeremiah Bryksa from the Northern Alberta Institute of Technology. I'll be talking about microplastics sampling development.
Hello, everyone. Can you guys hear me and see my screen okay?
Looks great. Sounds good.
All right. So thanks, everyone, for coming to listen, and thank you for the invite today. My name is Jeremiah Bryksa. I'm a microplastic researcher from the Northern Alberta Institute of Technology. We're a polytechnic college located in Western Canada. And I'm here today to talk to you about our high throughput application of ASTM D8332 and the microplastic sampling we do in our freshwater river. All right, so just to kind of paint the picture, we're studying the North Saskatchewan River. It's one of the largest freshwater rivers in Alberta. And there's a lot of challenges when working with this freshwater river. So it can have highly variable flow rates and high suspended solid loads. So this can be challenging to sample microplastics classically with nets. It's kind of in line with the previous presentation. When you have high flow rates like this and high suspended solid loads, likely your nets will clog, tear, or rip, especially if you use small mesh size. And for our project, we're looking at sub 100 micron particles. So the classical methods weren't really going to work with us for this project. So back in 2020, in August, ASTM published a method titled ASTM D8332. I saw from the previous notes that this was discussed before, but I'll just kind of give a quick overview of it. Basically, you pump large amounts of water, so around 1,500 liters or more, across a cascading stack of sieves. So the sieves are arranged in decreasing size, so the water trickling through will collect all the different particles in their size classes, and it'll decrease the chance of any one sieve getting clogged, especially the lower sieves. So when we read this method, we knew this was how we had to sample for our project. So this is a very practical way to sample rivers like the North Saskatchewan, and as well, it offered us the opportunity to create a large-scale data set using standardized methods, and that way other people can use their data and put it into like a global model of microplastics. So involving our sampling campaign, we have 12 sites along the city that we're sampling in. So the North Saskatchewan River passes through the city of Edmonton. It's a highly urbanized section of the North Saskatchewan. So we're studying various places within the city of Edmonton to find out where microplastics are coming in. So we do a lot of hiking down to the river, and we have lots of different sites that we like to sample in a day. So when we were designing our sampling system and sampling campaign, we set out 3 strict sampling system requirements. So the first one was we wanted to build a system that's lightweight and portable. We want to be able to hike around with it and access any spot along the river valley easily. So we need it to be lightweight and fit into backpacks. Second, we needed to have its own power supply. In the ASTM method, it was made for sampling wastewater, and at the wastewater facilities, they have ways to plug into power. 120 volts, but we don't have that luxury along the river. We want to be able to sample again wherever we want. So we want it to have its own power source. And last but not least, it has to be plastic free. The last thing we want to do is contaminate our samples with our own equipment. So those are the strict requirements that we set out when we designed our system. So this is what our system looks like. This is an image from one of the a paper that we're working on publishing in the near future. And I'm going to walk you through the system here. Sorry. So starting on the bottom left, we have an inlet, and we pump large amounts of water across a cascading sieve stack that you can see on the shore here. So we have an inlet, which is a 3/4 inch stainless steel tube that we face into the river flow. And we pump water through our plumbing. Our plumbing is modular 4-foot sections of 3/4 inch stainless steel tubing as well. So depending on how far from the shoreline we need to sample, we'll add multiple extensions. We all drive Honda Civics, so we can't really bring 20 feet of plumbing. So we add it as we need it based on the site requirements. We don't want to sample stagnant water. So we'll go out about usually 12 feet from the shore to be able to sample a nice moving water stream. So if you look at the expanded view here, we have a pump, which is a centrifugal pump. and it's powered by a 12-volt lithium iron phosphate battery. We have some flow controls and some electronics housed in our sampling case. And we pump the large amounts of water, 1,500 liters or more, across the cascading stack here. So it's just expanded, you can see. The stack is housed in an aluminum table that can be dug into the ground along the riverbed. It can also be set up over top of the river, so we're not eroding the sediment as we're pumping 1,500 liters through it. So that's one useful tip here. So we pump the water through the sieve stack, and on the right here you see a blank sieve that doesn't get water on it. So that's how we calculate our blank contamination, our field contamination. So that's really important to understand if you're contaminating your own sample and what that value is. We have the option to add a flow meter on the outside, and I'm going to talk more in detail about that. Just one last point I'll make. The system is fixed in place. So once it's set up, it's fixed in place. That allows you to stand away from the system. So you can stand far upwind or far downwind. So you're not really contaminating your sample. And as well, the fixed system allows for a really consistent flow rate. So the flow rate doesn't really change throughout the course of your sampling. So this is what the system looks like in real life. So we have our river inlet here fixed in with the stake, and our sample system is set up in the river, so we're not eroding the sediment as we're pumping all the water through it. We have our centrifugal pump and our sieve stack there, and the sieve table is just sitting there. So one important note is the river inlet is situated 1 to 1.5 inches below the surface of the water, and I'll talk more about that in a second. So just a couple of points on the components. The main components are the centrifugal pump and the lithium iron phosphate 12-volt battery. So we have them housed in these waterproof cases, so we can easily carry them to the field. So you could carry a battery and a pump in each hand, and it makes hiking really easy because you have a nice weight distribution. All the electronics are housed in the pump there. So you can see on the left, we have a knob that controls the flow, and we have a power connection on the right there. So that's a special IP67 rated power connection. So it can just connect into the battery, and it's gives us a lot of protection when working near the water for the electricity. Yeah, the lightweight and easy to carry. So we considered many different types of pumps for our system: diaphragm, peristaltic, and submersible. But most pumps failed to meet all our design requirements. Either they're too bulky, too heavy. A lot of them didn't run on 12-volt power, and then many contained plastic components or were just made of plastic. So that's why we settled on this centrifugal pump there. So these are our sieve. This is what the sieve stack looks like. So we use 4 sieves, a 5mm, a 500 microns, and the 500 micron and up particles are treated differently in the lab. And then we have a 125 and a 45 micron sieve. You could go lower. You could go to 20 microns if you wanted to, but our lab process is validated at 45 microns. So that's the smallest size that we use. And then the blank would be situated in the second slot of the sieve, and it would just be a spare 45 micron sieve that's cleaned in the lab, clean room cleaned, and you bring it out and you kind of open it when you start your sample, and then you can bring that back to the lab, and that's your field blank right there. Okay, so just want to talk about flow. So I said we're high throughput. How fast are we actually? So we can pump at around 33 liters a minute. But we can pump faster. So we can do a 1,500 liter sample in around 45 minutes. So that's pretty high throughput, I would consider. And I just want to give a couple of points on how you can calculate flow. So we have 3 methods to calculate flow. One, it's a very crude method, but it works really well in the field. So we have a bucket that's a fixed volume bucket, and we time how long it takes to fill up, and we do that in triplicate, take an average, round up. So it's not really scientific, but it works really good. Second, we have a turbine mechanical flow sensor. So that's you can see it in the picture there. So we just put the sensor or the turbine in the flow, the outlet flow, and we can calculate a liters per minute based on the revolutions. There is an instrumentation way to do it, but one point that I'll make is we found it quite challenging to find a suitable flow meter that we could hook up in line. that wasn't made of plastic and that operated based on our power requirements. But we did find this gray line portable flow meter. It's a Doppler sonar, so it sits on the outside of the tubing, and it sends radar into the tube, and it can calculate transient time as particles pass through it, and it can give an accurate flow rate. This is probably the most accurate way to do it, but it's also the most expensive way. This flow meter alone can cost more than the entire system plus your sieves and extra to build. So depending on what kind of budget you may have, you could get around it. I think based on our data, you can get accurate flow without doing this, because once you understand the flow at the start, it doesn't really change in the course of 45 minutes. So you can work on that. But if you wanted to have a sensor, that's what you can use, that sensor there. So over the course of last field season in 2021, we trialed a lot of different designs and modifications. So we made many procedural and design changes, and we finally tuned it all this summer as well. So you can see the system in there. It can be operated with 2 people. As far as the optimizations and validations, so we optimized various plumbing configurations, different types of tubing, corrugated tubing. We tried different operating and flow conditions. We characterized the field contamination levels, and it's pretty good. You can get, in the course of a sample, you can get as low as 10 particles, 10 particle contamination. So it depends on your wind and your field clothing, but we think that that's acceptable numbers. We ensured particles were not falling through the sieves that should be stuck on there. With a high flow rate, 1,500 liters in 45 minutes, that's a lot of water going through the sieves. We thought that it may be pushing particles through that should be retained on the sieve, but it doesn't. So we'll be able to provide that data in our publication when it comes out. And we developed various quality control procedures, things to do and things not to do. So as far as limitations, just wanted to highlight a few limitations with the system. While it does work really good to collect large amounts of plastics, we do sacrifice some things for the high throughput. So one of the things that can be challenging is the priming of the pump. So you can't just stick the system into the river. You have to wade in and you have to prime the pump. So what that means is you have to remove all the air bubbles from the system and make sure there's enough water back pressure to begin the centrifugal pumping. It can be done in minutes, but it is just something that you have to consider. One limitation of this pump is that if it sucks in air, it will stall out. And if it stalls out, you have to go prime it again. And it's not the best to do that when you're collecting a sample. You want a very consistent sample. The more time you spend around your sieve stack, the more possible, the higher the possibility of contaminating your samples. So you want to avoid that. So if there's a boat coming, there's a procedure we can do just to pause the sample, but make sure the flow stays the same. Or if there's like a big wave, it might stall out. So that's a limitation on it. There is a difficulty sampling the surface because it has to be situated 1 to 1.5 inches below the surface. We're not sampling the surface as effectively as probably we should be. So we're working on that for our next revision of this technology. And one of the limitations as well is any particle that is stuck into the sieve that cannot be rinsed off in the field with a reasonable amount of water, which is small still, but it is there. So that is a limitation as well. So to talk about, to summarize in an overview, we created an optimized microplastic freshwater sampling system that conforms to ASTM D8332. It's lightweight and it's portable. It can fit in a backpack and you can hike down with minimum 2 people to carry the full system. It has its own power source and it is plastic free. So this year, we built 2 systems actually. So we have a duplicate of the system and it opens a lot of cool sampling scenarios. So I'll just go over this. On the left, you see the dual stack sieve, and the right, you just see a single stack. There's our good old trusty calibration bucket, and you can see the pump and the battery house there. It's waterproof, so we're not really too worried about working in the water. And on the right there, you see our sample containers. So we just rinse into the sample containers there. Those are glass containers. So having two systems opened a lot of cool possibilities for sampling this summer. So we could set up a system on either side of the river and sample at the same exact time. So if there's different flow on either side of the river, we could, and there's probably different microplastic concentrations. So we're able to capture a snapshot at the same time. Using boats, you could sample the mid-river and the shore at the same time as well. And one of the really cool things that we've been doing this summer is any effluent or any pipeline that's putting water into the river, we could set up the sample directly in the pipeline and set up a sample either before or after the effluent, and you could get a really good understanding of what the effluent actually is discharging into the river and compare the two samples. So that's been a lot of fun for us this year. So just a couple pictures of what the system looks like in real life. This is just one of our sites that we look into. So you can see the system's pumping over the water. We're not eroding the sample or the shoreline. What do we have? So we're 12 feet out into the river there. And it's a beautiful day for microplastic sampling. So one of the things that we did this summer is we worked with our industrial partner, Interpipeline, and they have a very highly trained crew of marine operators, boat operators, sorry. And we drive around our downtown municipal region and we just look for pipelines that are on. The boat guys dropped me off. I set up the system and we sampled directly in the effluent, like I said, and then the boat team can sample the mid-river there just to see how it's dispersing. You could sample off a boat. There's a little bit of optimization that needs to be done still, but we can get a pretty good sample off a boat. So just a couple quick facts here. So we're capable of pumping 1,500 liters in 45 minutes, but we've done so actually in 35 minutes, so we can get it going pretty fast. We can from a hike from the river valley onto the shore. We can begin setup, calibration, and priming within 8 minutes. So it's pretty quick setup once you get the hang of it. You can quantify field contamination very accurately with the field blanks using this method. And we're weather resistant. So actually we could sample while it's storming because of our system is pretty weather resistant. I know there's a lot of research questions as to like what happens as there's a heavy rain event in the municipal region is washing stuff into the river. So we're able to get those types of samples. I just have 2 more slides. So what we're working on right now in the future, so we're working on our scientific publication. It should be out next month. So we'll be able to share that and hopefully everyone can read that and give me some feedback. We're working on training and tutorial materials, so you could download videos and watch how we do it, some do's and don'ts and some safety tips and that kind of stuff. We want to develop a technology to be able to sample the surface more effectively, and we have a couple ideas, so we'll be working on that this winter, sorry. And we're also working on the next generation of this technology. So just the final thank you slide. So thanks again for allowing me to present and inviting me to this committee. My name is Jeremiah Bryksa. I'm a microplastics researcher from the Northern Alberta Institute of Technology. So we work in collaboration with plastic producers in Edmonton. We work with Interpipeline and Dow Chemical Canada, so 2 of the largest plastic producers in Canada. And we have a coalition called the Plastic Research in Action, and we work together to solve various issues around plastic waste in the environment, and technologies to reuse and recycle plastic and incorporate plastic into other materials. So for more information, you can just check out nate.ca/PRIA. And yeah, I'll take some questions before we turn it over to Anne, my other Canadian colleague.
Thank you so much, Jeremiah. Really fascinating to see what you guys are doing. As always, people can just raise your hand, unmute. I think we do have one person with their hand raised, Sutapa.
Yeah, thank you for the presentation. It was very nice. I just had a question, Jeremiah. When the flow of the water into the sieves to collect the potential microplastics or whatever one is looking for, is it possible to, because like I think you mentioned during your presentation that the flow is fairly high, so it falls, and you have tested that it does not force plastics through. So I was thinking that would it be possible to have a sieve-like container higher up so that it breaks up the flow and then collect it into the subsequent sieves. So the higher up sieve or something that is not really so much for collection, but you could go back in there and check very large materials may be stuck in there, but that breaks up the water and it flows all over the sieves below.
Yeah, actually, that's what's happening with this method. So the top two sieves are 5 millimeters and 500 microns. We don't really care about that sieve. So the 500 microns, in our opinion, breaks it up enough. But you could add a 300 micron as well. I think that's actually in the ASTM. But yeah, that's the beauty of the ASTM. You can add whatever sieves that you want. I think the 500 microns breaks it up enough, and the 125 definitely breaks it up before it gets to the 45. So that, I think, allows you to pump the large quantities of water through it without the sieves clogging up. Yeah, so I think it already is doing that, in my opinion.
Yeah, the only thing the sieves, they're stacked on top of each other, right? So the water that falls through may not break up in the second sieve below as much. If you had another sieve at slightly closer to where the water is coming from and the lower collection sieves a little below, then the breakup of the water would be that's what I imagine. I haven't done it, but the breakup of the water would be more general, like that's just a thought.
Yeah, no, that's a good point for sure. Thank you.
I've got one question from the chat, which is, have you considered incorporating benthic or substrate samples alongside the surface water samples?
Sorry, repeat that again.
Have you considered incorporating benthic or substrate samples alongside your monitoring just to see the correlations?
I actually don't know what that refers to. Sorry.
Oh, like collecting a sediment sample as well.
Yeah. Oh, yeah. So our project is we have a large project. I didn't really get to talk about the project, but yeah, we take water chemistry samples, we take soil samples. The sediment actually is quite hard to work with along our north in Alberta, and specifically in our river there. So we're focusing on the water samples. They are pretty hard to work with, but we got the hang of it. But yeah, we do have sediment samples as well. Hopefully we'll be able to get through that with our funding.
Very cool. And related to that effort, I know that the Southern California Coastal Water Research Project is wrapping up a method validation for sediment. So that'll be coming out soon. Awesome. Thank you so much, Jeremiah. And if anyone has additional questions, feel free to ask them in the chat. And we'll go to our next speaker, Dr. Anna Posacka from Ocean Diagnostics. Correct me if I said your last name correctly.
Thank you, Scott. Let me just get myself set up here. Hello, good morning, everyone, wherever you are. Just a second. I think I'm up now. Thank you, Scott, and thank you to the chairs of the subcommittee for the invitation and an opportunity to connect with you all today. My name is Anna Posacka, and I'm the Chief Scientific Officer at Ocean Diagnostics. I am going to present to you about the novel sampling technology that we have developed specifically for the purpose of microplastics research and monitoring, with a focus on nearshore habitats. And I'll talk about the technology, and I'll also highlight some of the research projects in which it is being applied and validated. A bit about us. We are a Canadian company. We're based on Vancouver Island. We have an environmental mission, and we seek to empower stakeholders in academia, government, industry, civil society, and the communities with the right tools to fight plastic pollution and biodiversity loss, which we understand, of course, as some of the greatest environmental and global threats in the present day. And the way that we do this is there's 4 ways in which we do this. we developed technology that's designed to enhance the throughput and quality of microplastics and environmental DNA sample collection, analysis, monitoring, as well as data visualization and communication. And one of that technology I'll be discussing today, but we have a suite of instruments and technologies that we're currently working on. These technologies are designed to overcome the unique challenges that come with collecting reliable information on those two types of threats, the types of samples, but also to enhance and accelerate the pace at which we can collect quality information and share that within the community. Our team also offers a range of spectroscopy-based analysis of microplastics in different environmental sample types, as well as microfibers. And we support the workflow starting from sample collection and designing an effective sampling study all the way to processing, analysis, and recommendations on the information that was collected during sample analysis. We see the members of the general public as key in environmental stewardship. And so we are developing the tools needed to allow them to participate in creating change, in collecting research data or the data that can be applied in research and decision-making on microplastics specifically. And if you're interested more about that, we've just released 2 reports. You can find them on our website. I'll leave some information at the end of the talk about on the results of our pilot study on Vancouver Island in Canada, in which we've developed technology for community science monitoring of microplastics on sandy shorelines and applied it in the study of 10 different shorelines, beaches on Vancouver Island, to help the local community understand what the priorities are for microplastics and what are the potential solutions. The other ways in which we hope to empower everyday people in participating in research and creating change is also through education. So we have conducted an educational campaign last year with Canadian experts and microplastic pollution researchers to help the public better understand the issue and understand them where they can play a role in addressing it. And in that process, as well as the pilot study, we have developed a toolkit, which will be released in the next few weeks on a toolkit for community science on microplastics, on sandy beaches that includes educational resources, the technology, as well as guidelines and tips on how to create change within at your community level, collect the data, share that data within your community, but also on the global database, microplastics database that we've created for this project as well, where those communities can now, individual communities can connect with others around the world and share that information. And last but not least, we believe that collaborations will be essential in creating change and finding meaningful solutions to the issues of biodiversity loss and plastic pollution. And so we form partnerships with different organizations, some of which I will be highlighting today in my talk, to tackle the problem collaboratively. And so I'm very excited to be talking to this community today. And I would love to hear back from any of you if you have a project in mind or a technology development project in mind that you would like to collaborate with us on. So onto our technology. In developing our technology, we had to take several challenges into consideration. One is, of course, contamination. Microplastic samples are extremely prone to contamination in the field and during processing. There's a high human power requirement, as we have discussed already in this meeting, involved in collecting and analyzing microplastic samples. We are working with a mixture of contaminants. By definition, there is an extreme diversity when it comes to microplastics, diversity in shape sizes, polymer chemistries, and so on. But also overlaid on top of that is this environmental variability and the influence that proximity to a source can have on microplastic distribution and composition. While microplastics are prevalent, they are nevertheless trace analytes. So compared to anything else that we find in the environment, all of the other particles, they are present in these extremely low concentrations, abundances. And of course, we have standards that are still evolving. And those challenges, the negative impacts that those challenges have are that we have data that in published data that oftentimes perhaps does not have the quality required for decision making. So that is being hindered right now. There's no one-catch-all method that can effectively measure all of the different types of microplastics at any given time because of this extreme diversity. Pre-concentration and extraction of microplastics from environmental waters is necessary to detect them and quantify, but how much is enough? What is that minimal sample size? It's still not clear. And due to the lack of standards, or the fact that they're still working on them, though many, including the drinking water ones developed through this initiative, are available now, we have this issue whereby the data in published research is not directly comparable. And so therefore it's very difficult to use that data to develop technology and to develop meaningful solutions. And so we see that in order to overcome those challenges, we need a technology that will help us to protect our samples in the field, but also enhance our ability to collect those samples. Methods, both technologies and methods to collect those samples and process them need to be targeted and geared towards the goals and the needs of the project, the study, regulation. But we also believe that it needs to be, that microplastic load and composition also needs to be taken into account. In order to develop those targeted methods, there's a need to improve the state of knowledge on microplastic levels and contamination in the environment. And in concert with that, we as a community need to better understand what are the trade-offs and strengths and weaknesses of the different sampling strategies using comparable analytical techniques. And so where does our technology fit into this? I'm having an issue advancing, there we go. I would like to introduce you to Ascension, our depth profiler. Ascension is a portable unit that is light, it weighs about 18 pounds, that allows you to collect or filter water in situ down to 400 meters within the water column. So it's designed specifically for environmental water in situ filtration. And that it's a closed system. So we have here, let me just move my bar here. So it consists of a submersible pump, a few sensors that allow us to monitor the depth, temperature, as well as the flow rate at which the water is being pumped through the 7 different channels that you can see here on this in this picture. So it consists of 7 flow channels that are into which we have integrated 2 sets of filter holders, and they can hold 47mm filters. And pardon me. And there's a tether that is supplied with this unit that communicates, that allows for the communication between the Ascension and the researcher on board the vessel, or in a kayak, or at the pier. So this device is easily deployable because it's small and lightweight. We've developed it for deployment from different types of boats, vessels, but also from potentially a pier or a marina. So as a result, it provides a lot of flexibility in which samples for microplastics can be collected. And as I mentioned, it does allow for real-time communication with the equipment in the field. You can also set it up for autonomous sampling, whereby the unit is installed, maybe to installed in the field, and then it's set up for automated sort of collection of filtered samples within a day or over many days. And as you can see, with this closed system, we're filtering water in situ. The samples can be processed on board under the laminar flow hood, a portable laminar flow hood, to minimize sample contamination. And so we have, in order for us to best understand where our technology will have the greatest impact, we've established a multi-partner research program that aims to compare different sampling strategies in coastal waters with low to high microplastic contamination, assess sampling requirements such as the sample size, replication, frequency in relation to environmental microplastic condition. And our final goal is to empower the efficient monitoring of microplastics in British Columbia's waters and contribute to the efforts of our local partners to identify sources, risks, and relevant solutions. And we're working with University of British Columbia and Department of Fisheries and Oceans, Canada. So a little bit of more detail about our research program. A lot of this work is still ongoing. We have 4 different projects through which we're trying to understand microplastic abundances in a wide variety of environmental conditions and levels of urbanization. So we're working on Vancouver Island. Our team at Ocean Diagnostics using Ascension depth profiler to sample water in various harbors and coastal environments using different types of meshes with volumes up to 100 liters, because we find that this type of volume currently is an optimal amount for this equipment, although it's possible to process more. We're working with our partners and the lab of Dr. Sarah Dudas at the Department of Fisheries and Oceans to use Ascension in monitoring of microplastics in British Columbia's conservation zones. And here you can see a photo of Ascension, of a recent deployment we did in the Jervis Inlet in British Columbia, which is a part of the rockfish conservation protection habitat here in Canada. We're also working with the industrial ASTM sampling method that Jeremiah was discussing earlier, and the processing method, working to understand, to compare this methodology and to collect samples in these different range of habitats, to really understand, what is that minimal sample size that's required in order for us to accurately depict the level of microplastic contamination, depending on where you are. And we're working with University of British Columbia, who are using the McLean pumps, as well as an in-house engineered device to sample both surface water and waters down within the water column. Again, throughout all of these different projects, we're using different sample sizes and meshes, and are hoping to learn about, and also keen to share that knowledge in the future, to learn about both pollution levels, microplastic pollution levels on our coast, and how that relates to proximity to different sources, of plastic pollution, but also what are those optimal sampling strategies that will allow us to be more targeted with our sampling for microplastics and save our time and money. And so I would like to thank you for listening. And if you have any more questions about our technology or other solutions that we're currently working on and are interested in collaborating, I encourage you to reach out. As I mentioned, a lot of the research that I've highlighted is still ongoing. We hope to have some results to share end of this year. Best way to reach us, you can find some information here, but I also look forward to any future meetings where we may be able to share the data and the knowledge that we've learned through these projects. And last but not least, I'd like to thank to our partners and funders for working with us on tackling plastic pollution and biodiversity losses. And thank you so much.
Thank you, Anna. We have time for just like one quick question. Somebody wants to raise their hand. We do have a couple on the chat. One about if you're collaborating with the faculty of University of Victoria's Marine Biology and Oceanography program.
Pardon me, I missed that question. Sorry, can you repeat that?
Sorry. The question is whether or not Ocean Diagnostics is currently collaborating with the faculty of the University of Victoria's Marine Biology and Oceanography programs.
Thank you. No, thank you. Yes. Not this particular department. We are working with the CamTech facility, the material sciences facility at the University of Victoria. But I'd love to hear from, I'd love to connect with the person who asked this question.
So in the interest of time, I think we're gonna move on to the next part of the agenda, but if people wanna ask questions in the chat to Anna, that'd be great. Thank you so much for presenting. Fascinating work. So next we're going to hear from our work group leads. We have the consumer messaging work group with Brent Alspach, Terry Slivko, and Alma. Remind me how to say your last name.
Betragic.
I will try to say that. Betragic. Okay.
Very good.
Okay, and so we'll hear from Alma's team first, and then we'll hear from Shelly Walther and Shelly Moore for the sampling and analytical methods playbook work group. So Alma and Brent, I'd like to give us an update.
Okay, great. Do you guys see my screen?
Yes, looks good.
Great, perfect. So hi, everyone. So I know we're a little behind on the schedule, so I will try to move through this as quickly as possible. I'm giving a very quick update on where the consumer messaging work group is going, and also using this opportunity as a recruiting tool. We're always looking for additional support and folks who are interested. So after this presentation, if this is something you'd like to contribute to, please reach out. So with that, let's dive in. I first wanted to offer a quick refresher on the goals of the consumer messaging work group, particularly for folks that might have not been with us during the larger group meeting back in June, and then go into discussing what I'll call the guided brainstorming session that we had last week as a group. And then jump into the outcomes of those sessions and conclude with some action items, the next steps. So first, to review the goals of the consumer messaging work group, they are two-pronged, and the first is to develop language for utilities to use in their consumer confidence reports, which is particularly relevant for California, where where utilities will be sampling, and potentially any other states around the country that either sample voluntarily or by decree. And then the second goal of the consumer messaging work group is to provide this kind of contextual additional reference material for utilities, which could be used to supplement their CCRs if they choose to do that. So jumping into the guided brainstorming session, last week the group had a meeting, and our discussion centered around a few key questions that we hope to answer. We did not get to cover all of them, but I will summarize those here. Here are the ones that we did get to on that meeting. So the first one here is the discussion really focused on the general CCR language provided by the state, looking at what's been provided by the state, and kind of having a brainstorming session about what that means for the consumer messaging work group. Second, how much content should be developed. Third, what behavioral changes, if any, are we hoping to promote through the CCR messaging? And then finally, how we can leverage this unique scenario to increase public trust in drinking water. So as we go through this presentation, I'll work through these questions one by one and kind of summarize, capture what the group's discussions were. And of course, if there's anyone on the call from the consumer messaging work group, if I forget anything, please do jump in. Here are some of the questions that we did not get to. So what types of information should be included or specifically avoided? What are the intended messages that we're trying to convey with consumers in the CCRs regarding microplastics? Should our product or deliverable include background or context as an FYI for utilities to craft their own messages, or should we craft that specific language for inclusion, and maybe both? So the group did mention here the idea of maybe providing template language in table format, something that's very easy for utilities to use, and then linking to additional material, perhaps on a web page. And then finally, the additional questions we hope to tackle in the future, some are focused on risk communication. So what additional risk communication of microplastics would be relevant, what additional research on that would be relevant, and what strategies have proven useful in the past that might inform our approach this time. So jumping into that first question, presented on this slide is the state-generated language that will be provided to utilities as guidance, which was covered on the last call, but wanted to include it here as a refresher. So our group's task is to supplement this with potentially more information, either verbatim or conceptual guidance. So the group reflected on this statement And those discussions are summarized in the bullets here. So note that while the monitoring data and results are required to be in the CCRs, the accompanying language is recommended but not required. And one of the things that the group specifically discussed with regards to this state-generated language is the choice of words around the highlighted portion here, some types of microplastics. So we concluded that it is important and necessary to have this distinction to bring really to attention the nuances of microplastic toxicology. There are many shapes, many sizes, materials, et cetera, and most laboratory studies are done using one type of particle. And during the call, it was the example was polystyrene spheres. So it's important to make sure that this kind of boundary language is in there, reflecting study limitations and study design. The group also echoed the importance of ensuring that the material we generate be reflective of the most current health studies. And to this end, Scott did share a resource on the call with us that was published just last week. You see that on this slide here by the World Health Organization. And this is a 2022 study that builds upon a prior 2019 report reviewing the state of the evidence on microplastics in drinking water and their potential impacts on human health. But in order to kind of more holistically assess potential health risks, this 2022 study aimed to look at exposure from various sources of the environment, including water, but also food and air. And the report is really a great resource for reviewing references. The authors looked at evidence available published through December 2021 and assessed potential health risks based on that. Also worth noting is that as a result of this work, the WHO identified research needs and gaps and the scopes of work for future studies to address some of the current uncertainties. And that study is linked on this slide for reference. And thanks again, Scott, for bringing that to our attention at the last call. The next action item here, another resource that the Consumer Messaging Workgroup is working with and using, of course, is the California CCR Reference Manual for water suppliers. So the March 2022 update of that document is linked on this slide. And this document can help us understand kind of the language that's already in there for other contaminants, perhaps as a model or guide. But the important distinction that the group did make is that CCRs are going to refer to MCLs and ALs, for instance, which are not currently relevant for microplastics. So how do we kind of navigate some of these columns, some of these expectations that consumers will want to read about and have answers to in light of the uncertainties that exist? So the second question that we tackled was how much content should be developed. So what should the outputs of that consumer messaging work group look like? And one of the few ideas thrown out with regards to this question was just a table, like I mentioned before, templatized language that would be easy for utilities to use, but also including the necessary accompanying text and additional material linked to a web page for anyone that's interested. Whether that deliverable is, whatever that deliverable is in the form of, the group did kind of echo the sentiment that the main aim, of course, is to build tools to help utilities gain confidence and transparency with regards to microplastics. So TBD on this question still. The third question we dived into, the group discussed what behavioral changes, if any, we were hoping to promote through CCR messaging, and whether there are, we shared thoughts about what a CCR's fundamental identity should be, and how, if we did want to incorporate public education, how do we maintain that fundamental identity of communicating what is in your water and the associated health risks while complementing that with public education or behavioral change. And this could be a future goal of the consumer messaging work group. So assessing the, let's say, assessing and understanding the readership of CCRs, for instance, could be a good first step towards the eventual behavioral change goals. And the fourth and final question that we tackled as a group that I'll highlight in this presentation focused on how we can leverage this unique opportunity to increase public trust in the drinking water. So some of the sentiments that the group shared are summarized in the points here. For instance, folks mentioned that when microplastics are reported in consumer confidence reports, they will need to be explained and contextualized beyond just a simple brief health impact statement. And for instance, this could also be a living document. So the group talked about the language that's in the CCRs evolving over time. So as the 4-year microplastics monitoring program in California proceeds, maybe that language can evolve based on information from the year prior. We brainstormed whether those sampling results from the first year would impact the types of information that is important to convey in subsequent years, of course, with the complexity here that those results will likely be system specific. So that's another idea that the work group will be ironing out. But nevertheless, the CCRs do offer a opportunity to develop public trust between utilities and consumers. It's an important form of communication and perhaps dialogue. And there are currently pending changes to the CCR requirements by the EPA, and it might be required that utilities publish CCRs twice a year. So considering what that might mean for the consumer messaging workshop, we might have twice as many opportunities to communicate with consumers. So this slide just summarizes some of the potential changes to the CCR requirements. Currently, utilities would have the option of sending the same CCR twice during the calendar year or producing a new CCR every 6 months. And there are, of course, pros and cons to each of those approaches. Pros of delivering the same CCR twice would be that it might potentially reach more consumers. And the con of that would be that it might not contain as up-to-date information as possible. And then on the other side, if utilities decided to publish CCRs based on a six months of data or twice a year, it might be more timely information, but it could also create a burden for states and systems.
Hey, Alma, just in the interest of time, would you be able to wrap it up in the next minute or two, please?
Yes, of course. So to conclude then with action items and next steps, I'm going to go through this pretty quickly. We already covered some of the resources that the work group will be using. And next week, the leads and co-leads will be meeting to kind of synthesize these group conversations and thoughts and discuss how to use that information to inform more concrete next steps. Again, there's plenty of work to be done, and some of those outstanding action items are listed here. So identifying specifically our goals. Are we trying to educate, convince, comfort the CCR readers what that work product deliverable really looks like? The platform preference for dissemination of that information. So a lot of outstanding work to be done. And in the interest of time, I was going to provide a quick update on the parallel WRF effort, the Water Research Foundation 5155 effort. I will abbreviate that just to say that currently, as of now, we are in that task. We completed task 1, information collection, and are gearing up for the task 2, strategic planning workshop, which is scheduled as of right now for the 15th, where we will be looking into some of the utility experiences, reviewing the knowledge from aggregated from task 1 and drafting messages that'll then be used in the consumer survey. So I think that is all I had for today. So if there's anyone on the call that would want to mention something that I forgot from our meeting, please do. I'm happy to take any thoughts, comments, or questions.
Thank you, Alma. We do have time for like one quick question. Somebody just wants to raise their hand or unmute. Hearing none, I will move over to our other work group lead, Shelly Walther and Shelly Moore.
Can you all see the presentation?
Looks great, thank you.
Great, great. Well, it's nice to see you all again. I have just a very brief update so we can move along. The first really exciting news is that we have, in the last meeting, I kind of brought out that we were looking for a co-chair, and Shelly Moore immediately stepped in and said, hey, I'd be happy to do that. It really works well with some of the work that she's working on right now. And Shelly and I have worked together for decades. I don't want to age us, but Shelly, please introduce yourself and say a few words.
Yeah, I'm Shelly Moore with the Moore Institute for Plastic Pollution Research, and this is of interest to me for a number of reasons, but mostly because I also was co-author on the California monitoring methods playbook for trash monitoring. And so I want to make sure that some of what we put into that book also gets recorded in this one, and I'm happy to be working on it. Thank you, Shelly.
Thank you. And you know, that the trash monitoring playbook was the inspiration for the microplastics monitoring playbook. So it's going to be a great fit. So as Shelly was saying, that's one of the basic, just a brief review of what we've recap of what we've talked about before for those of you who may not been with us in previous meetings. The microplastics monitoring playbook, or the MPMP, will be a living document, and its basic tenet is to build on the best available science and build rather than create fresh. And I think that that's going to be really powerful for, we have so much good information and we need to put it together, and really a lot of it may be going back to some basics for representing statistically rigorous data, which the trash monitoring playbook does very well. Some other universal considerations in the playbook that transcend a matrix would be the study design, sample collection, data reporting and analysis, and reproducibility of the study. And I briefly introduced a straw man of the playbook and talked about some elements that would go into it, such as the study design would depend on the intended application. And so there are a lot of questions that can be asked, and that would help inform the study design. The use of precision estimates in quantifying uncertainty has come to light as something that's really critical. There is a paper that's come out recently. It's Wagner et al. 2022. Jeff Wagner is from the California Department of Public Health, along with Bill Robertson and Harry Allen from US EPA Region 9. They did a study using many different analysis techniques and compared precision estimates of each type, and have some really good take-home messages about what this means for future studies. And it's something that we can really use for future study design. And part of that is analyzing more than once and using that error estimate that you get to help you with future estimates, future analyses. We also discussed that data analysis can suffer sometimes from zombies, as Dennis Hensel puts it, and we kind of went through some of those zombies, and one of which that we've experienced a lot with microplastics is low sample size, because it's so expensive and time consuming to do analysis for some analysis types. you can run into problems if you analyze too low of a volume. And we've seen that specifically with wastewater. There's the figure in this slide kind of points to a meta-analysis of several different studies and a really strong correlation with low sample size showing higher numbers of microplastics. I really want to make sure that we're supporting the Scott Coffin and the DDW effort to carry through with the legislative mandate for SB 1422, the California Safe Drinking Water Act, microplastics. And so if, you know, there are a lot of elements of the playbook that would transcend matrices, but there will also be a focus on various matrices. And the first step would be drinking water, source waters and drinking water. So which would be possibly very different methods, analyses, depending on, you know, the matrix would matter. If there's salt, a lot of salt, ocean water, it would be different than ambient fresh water. So those are things that we're going to be looking at. And finally, the next steps, we are looking for some external funding, and we're working on, Shelly and I and others are working on that. And we're still working on the getting a very large Zotero literature database up and publicly available to, I think just the sharing of information is really critical for this. And there's so much, so it would be great to just be on an even playing field for that. And we're going to have we'll send out a notice of a work group meeting for November. And we'll focus on elements of data reproducibility. So that's all we have for today.
So much good work happening. Thank you so much, Shelly, for presenting. If we have any comments or questions, we can go to those. Feel free to raise your hand or unmute, type it in the chat.
I don't see any.
Hearing none. I wanted to give a brief update on the adoption of the policy handbook for microplastics and drinking water. So I'll keep it really quick. And then if anyone else has any other announcements, actually maybe that they can go first. Open to anyone, anything that people want to share, you can either drop it in the chat or just unmute and quickly give an update. Alrighty, well, I'll just give a brief update on what happened yesterday. Those of you that weren't able to tune in to the board hearing, yesterday the State Water Board adopted our plan for sampling and analyzing microplastics in drinking water. And this was an effort that really involved a lot of stakeholders, many of which are on this call. And so I really appreciate everyone's help that got us to this stage. This is a huge community effort. Just as a reminder, a lot of the research that has led up to this point was conducted through these collaborations, a lot of them being facilitated by the Southern California Coastal Water Research Project, among other partners. And we've since adopted a regulatory definition, done some method standardization work, and did a human and ecological risk assessment. So based on the work that has led to this point, we have been able to adopt a plan for how to sample microplastics in drinking water over the next 4 years, and what to do with that information. This is a 3-stage iterative approach. The first year is the pilot phase, which is currently happening. It'll be wrapping up next year. And this is largely focused on resolving some technical uncertainties with the sampling approaches that'll be used. We'll be comparing the ASTM method with an inline filtration method. We'll also be doing some range finding of contamination in different water supplies in California. And we'll be providing training for people that are going to actually go out and do the sampling, in person and virtual training. So if you're part of those water systems that is on our list of 30 systems, make sure you stay tuned. There will be an announcement soon about when you can get involved in those trainings. And then we'll be issuing monitoring orders to the systems on the list in the policy handbook for a 2-year monitoring program. It'll be quarterly monitoring where the systems will really just be looking at the source waters, and we'll from this effort we'll figure out what factors lead to contamination and where we want to do additional sampling, if any. And then phase 2 will be an additional 2 years of monitoring, looking at additional systems based on where we're finding likely contamination, and then also hopefully looking at the treated water to figure out how much is being removed by the treatment plants. I mentioned before we have this pilot phase. This is currently ongoing. We're evaluating this improved inline filtration methods, developing the sampling and analysis guidance handbook that Shelly just mentioned, training system operators, providing time and resources for ELAB accreditation, developing the data infrastructure, which was discussed earlier by Lindsay. That project is largely being run by the Moore Institute, and then developing this communication toolkit for water systems, as mentioned earlier by Alma. ELAB accreditation is now available. Just on Tuesday, we posted this. So if you want to apply to become accredited for running microplastics analyses, you can follow the State Water Board links. And there's currently 6 different fields of accreditation. These are for different size bins of plastics using different methods, either infrared or Raman spectroscopy. For phase 1, we'll be looking at mostly the large community water systems and wholesalers. There's a couple of disadvantaged large systems and a couple of state projects. And you can see we have fairly good statewide coverage, geospatial coverage. And based on some of the comments from the board members yesterday, we may be adding a couple systems to this list that are strategically placed around to get a good representation of the source waters used by most disadvantaged systems. This list that we have is not final. We want to hear from the water systems that are on the list and from the public in general. So we're holding a public workshop. It's going to be later this year, maybe early next year, to determine where the specific monitoring locations will be. And we'll be collecting input from anyone who wants to join that conversation. At this meeting, we'll be we may be able to provide exemptions for systems that would be redundant with one another or technically infeasible to monitor. And the final list will be approved by the Division of Drinking Water. I mentioned before that we're going to be comparing this ASTM method with an inline filtration method. This was discussed at previous meetings by Dr. Bob Andrews. And so if you're interested in learning more about that, just check out the Google Drive. You can see the slides and watch the YouTube recording. This sampling standardization project is being coordinated by SQUIRP in collaboration with Brown and Caldwell and the University of Toronto, Dr. Bob Andrews' lab. And then again, we have the sampling analysis playbook work group that Shelly discussed before. So I'll open it up if anyone wants to ask any questions, clarifying questions, that'd be great. Again, if you have any announcements that you want to share, feel free to do that now as well. Oh yes, the ITRC is currently writing a microplastics guide document. I believe that document went out for public review and they just closed it, but there might be still an opportunity to provide input if y'all are interested. Terry, did you want to say something?
Hi, yeah. Hi, everybody. I did have a question about the what the board's feedback was with respect to the open access data portal, if they said anything to you or it had any concerns about it.
The board members themselves didn't have any questions about the portal. They did have quite a few questions about the communicating information to consumers and the CCRs. they share the same concerns that the water systems do, which is they really want to avoid eroding public trust, and they're looking forward to the work that we're doing with the communication toolkit.
Great. You know, it was a very nicely done presentation. Kudos to you, Scott, and congratulations. Thank you. Thank you for enabling such a transparent process and working so collaboratively with us. We really appreciate it.
Likewise.
So Scott, for those of us that were maybe happen to be teaching in the exact time you were talking, the Water Board does post their meetings on YouTube, is that correct?
That's correct, yes. I posted it on Twitter.
Okay.
But the YouTube link, I can also drop it in the chat real quick. And I just had a question. The handbook was adopted by the State Water Board yesterday. And go ahead, Nick.
Yeah, thanks, Scott. And I also want to reiterate congratulations. Looking forward to keep working with you through all this. One question that did come, and I think you just kind of brought up with Board Member Firestone's call to add some other systems that are maybe not included. How will that be maybe balanced with the conversation around also removing systems that are redundant? That was the first thing that came to mind of like, well, how are we going to maybe balance that of like, anyway, I'll stop talking.
Yeah, that's a great question, Nick. And so what I'm thinking for the fall workshop and going forward to actually choose the monitoring locations is we'll be looking at the actual sources of water and looking into if we have a good representation of what most systems are using in the state, especially the disadvantaged systems. And that'll really help us refine that list further. So for instance, the major things that we're going to be looking at is de facto reuse. So systems that have treated wastewater in their source water that is not being covered by the recycled water policy for indirect potable reuse. And then we're also going to be checking out the SIC codes in the SMARTS database, which tells you the industries that could be potentially point sources. Those are the two main factors that we're going to be looking at, as well as proximity to other non-point sources, so like urban infrastructure, agriculture, that sort of thing.
Thanks.
And really looking forward to collaborating with you more on this.
Scott, I had one more question about the workshop in fall winter 2022. Is that going to just include all of the public agencies that are listed there? Or, I mean, how are we going to do that? I know maybe this isn't the right place to ask these type of questions, but it's on my mind. And if you want to take it offline, we can.
Yeah, I'd be happy to chat with you more in detail later, but really briefly, what we're thinking is we're going to have a staff workshop. So it won't be an actual board workshop. It'll be run by the staff, and it'll be open for everyone to join, but we'll make sure that the systems on that list will get notified. And ideally, it'll be like a couple-hour workshop where we can hash things out, but we may need to have like a follow-up conversation with stakeholders. And we may also have some like pre-conversations that are more like smaller group. And I'd be happy to work with you on that.
Of course. Thank you.
Awesome. Well, thank you all. Really successful and exciting meeting today. And we will see you all at the next quarter. I'll send out the meeting invitation pretty soon for that. Calendars.